Welcome, South Texas Section AICHE. I hope you've had a lovely dinner. We had such great compliments about the food and the camaraderie. So thank you all for being here. I would like to give a shout out to our future chair of the national group. Billy, can you raise your hand? Billy is one of our future officers. Thank you. Made the drive tonight from Freeport, so we appreciate you being here. So if there's any programming information for next year, Andreas is here as well as Billy, and that's thank you, Andreas. So thank you. The programs are being set, so if you have some ideas, this is who you go to. Thank you both. Okay, so I'm Julie White. I have a privilege of representing us as your local section chair for this year. And Andreas is our chair-elect who will be chair next year. And on that note, I will move us through our dinner meeting. So thank you so much for being here tonight. We have the privilege of having a great keynote by Dr. Powell. Joe is speaking on energy transition, hydrogen, circularity, and carbon management for the U.S. Gulf Coast. He's with the Energy Transition Institute of University of Houston, and as you probably recall, he's a Shell Fellow and retiree. Just a note that we do record our meetings, and they can also be updated or published to the website, and so you never know what these mics pick up, so just a heads up, and thank you for letting us do that, including your Q&A. So we have a few announcements tonight. I certainly just want to give thank you again to certainly the hotel for a fabulous meal, but most importantly to our conference committee. It's our 14th year, and AICHE South Texas Section started the conference, and it's just really a grassroots effort to make sure that we are encouraging our technologies that are applicable to our greater Houston or 28 and a half county engineers. And the feedback I've had tonight from those who are here for the first time or exhibitors are that they really like the interaction that we're able to provide at this type of conference. So thank you for making that possible. I give, again, a shout out to Alan Rossiter, Ian Glasgow, Virginia Sumner, Todd Caparizzo, and Justin Canna. Thank you so much. So we're halfway through our conference, and I want you to know we have just shy of 30 papers. More than half were presented today. We have over 20 session chairs, and it's just been a great opportunity for us. Thank you very much, Alan. Our sponsors are just shy of 30, or just over 20 as well. Thank you very much. So on Friday night, to close out this fabulous event, our YP group is hosting a social. So post-conference conversation, networking, and drinks are provided by the STSYPs at the Rustic in the Galleria. The address is 1121 Uptown Park Boulevard. So bring your friends and colleagues. No registration is required. If you have questions, you can direct them to Ram, who is our STSYP chair this year. Thank you. So you've heard me say it already, our STS AICHE membership is available through our website, but also as part of the national meeting or national membership registration that occurs annually. About this time every year, you'll be receiving your renewal, and we certainly appreciate you renewing for the local section. Not only do we provide the scholarships and recognition to our members with best papers and service awards, STEM support, K through 12 support, but we also have opportunities for continuing education. And the PDH credits that we offer are essentially every meeting but December. So it's typically, this one is one, but you also have the conference, and then we have customarily two, a pre-dinner workshop as well as a keynote that typically are sufficient to accredit for PDH. So thank you for our speakers through the years, as well as this year in particular. So great news. One of my favorite topics is, those of you who know me, I talk about this almost at every meeting. Dale Embry, Carol Schmidt, and over 8 other instructors are hosting the Chemical Engineering PE Review course in the springtime next year. It will begin February 18th, and enrollment will start coming up. Look for it on our website this month, and it'll close a few days prior to the start of the course. If you have any questions, our lead instructor is Dale Embry, and he's also responsible for curriculum. We've had great success with the likelihood of passing the exam based on studying for the course, and I'm a recipient of the benefits of the course as well. I don't know that I would have dedicated myself to the studies had it not been for the schedule of the PE course. So we have a big event coming up. It's one of the largest K through 12 outreach. Matt Kolodny is our point. Let's see, Matt, I'm looking for you. If you could raise your hand. Okay, thank you, Matt. Thanks. Standing's even better. So if you're interested in volunteering, Aaron Green-Colaco as well as Matt Kolodny are our coordinators for the event. We essentially have 2 teams, 9:30 to noon and noon to 4 at the Sam Houston Park. We coordinate our booth with the Engineers Council of Houston, and Matt is also seeking non-traditional chemical engineering approaches. For example, he's reached out to a college, San Jacinto College, to see if they're available to help provide some technology information on what it would be like to be operations technology. So I just want to commend Matt and his team for thinking outside of the box on careers that support our industry. Thank you for that. Absolutely. So one of the real neat things that the South Texas section is able to do is annual service awards, technical in nature as well as service. And so we have multiple committees. We have an awards committee. The executive committee has certain award responsibilities. Our young members committee, 3 chairs, that's the chair-elect, chair, past chair, have some responsibilities. And then of course our national group does for our like 50-year award and so forth. So this year, it's a great year for awards. We have distinguished service, young professional, and special service. This year, or this meeting, we're awarding one of those. I'd like to give recognition to our standing committee for awards for 2022, for service awards that were led and evaluated for 2021, and that's Tom Min, David Solarski, Matt Kolodny, Nitish Mittal, there you are, and Bando. And so thank you so much for your volunteering for this. It's such a great recognition. This year we have Gary Award that's awarded by our executive committee, the elected officers and directors. There's 9 of us. The Gary Award is really for science and education. We'll be giving that out next month to the winners. The Ekholm Distinguished Leadership Award, that is a subset of our DSA, our Distinguished Service Award, and that will be given out in December. Lifetime Achievement, big award, that will be given out next month. And the Churchwell Environmental Award was awarded to Tom Rim and provided at last month's meeting. So elections will begin the 2nd Tuesday of October. We will start out with the positions where we have nominees, and then we will continue from there. I would like to give a shout out to the nominating committee. That's our past chair is lead. That's Ramanan Krishnamurti. Tom Rim, who's a triple or quadruple past chair. Emily Jackson, well-known YP, Ram, and Aaron. Thank you again. Okay. So, backing up 1 minute. So our next meeting is November 3rd. So our elections will begin the 2nd Tuesday, and they'll go for a month through November. So you'll see on our website where you can receive a ballot link if you're a dues-paying member of the local section, and also we'll be able to vote at the November 3rd meeting. So Volunteering, we're always looking for folks who are dedicated to the South Texas section. And again, you'll see we have over 100 this year to do what we need to do. If you're interested in sponsorship committees, bylaws, governance committee, social media team, which is fun, or being like an IT volunteer, we do have the need for that, as well as continuous volunteering for certain events through the years, like K through 12. So I'll start out with the awards and recognition. Tom Min and I put these slides together, and I'd like to say that for 2021, we had a number of best papers, essentially 7 for applied best paper, 6 for fundamental, and 2 for in practice. And we were able to evaluate 15 of those. It's important for the nominator and the authors to be STS AICHE members. And so I'll let Tom speak about what applied, fundamental, and in practice means when he presents those awards on behalf of the committee. So Ramanand's not able to be with us tonight, so I'm skipping over this slide so he can have his chair appreciation at a later date. Paul had a matter come up, and so it happens when you're busy, right? But I would like to give recognition to Lucas Van Ruff. Lucas is our 2021 STS AICHE Outstanding Young Professional. Lucas volunteered as the YP chair in 2020 through 2021. He also has a past history of volunteering for AICHE. When he was at U of H, he was also the chair or president of their section as a student. He works in research that is on, for waste management, that's on renewable natural gas. And it is something that obviously he's passionate about. I remember sitting next to him at a dinner earlier this year, and it was just very impressive, his background and know-how. And so on that note, I'll meet you down here, Lucas. But I'd like to award to you the Outstanding YP. Thank you very much. Okay. Okay, all right. Okay, so I'd like to give appreciation specifically to the applied and fundamental judging team. There's over 20 volunteers who look at the papers. Matthew Christensen and Ryan Stevens of Shell, right? Tom, okay. Are our leads for the applied and fundamental judging teams. And here are our judging committee. So I'll just pause a little bit for our second slide. Okay. Our committee for best in practice is led by Tom Min, or chaired by Tom, with Bandu, Matt Kolodny, Nachish, Tom Rim, and David Solarski also. So before we go on, every year they do this, and I just want to give them a round of applause. Thank you. Okay. And now for the award. Okay. So forgive me while I did not practice this ahead of time. The 2021 STS AICHE Best Fundamental Paper is awarded for an advanced material article for June of 2021 titled Memory Seeds Enable High Structure Phase Purity in 2D perovskite Films for High Efficiency Devices. And our members are Professor Mike Wong and Amanda Marcial, Sadiq Lee, Samani, Zong, Wong, Hoffman, Fair, Katan, Evan, Kanatsidis, Blancon, and Mohite are the authors of this paper. Tom, are there any other words you'd like to share on the mic? Okay. So on that note, I'd like to have a round of applause and ask for our representatives to come up. Oh, thank you so much.
You don't need to walk down.
Okay,
No worries.
thanks. All right. You can tell we coordinated this well. Okay, so thank you very much. Appreciate you both being here to represent your authors. So our best in practice paper goes to Harry Escobar Hernandez and his team, Shin Papadaki, Dr. Joe Powell, Zhao, and Wang. And the paper is in the is in ACS Chemical Health and Safety in the July of 2021 article or publication last year. The article is titled Hazard Evaluation of Metal Oxide Framework Synthesis and Scale-Up, a Laboratory Safety Perspective. I'd like to thank Harry for your safety work in this field. Thank you very much. Thank you. Okay. Thank you very much. Okay. So on behalf of the three chairs, that's Ramanan Krishnamurti, myself, and Andreas, we have a very special award. The representatives are not here tonight. We gave them the option of essentially allowing us to provide a dinner for them at home if that was their choice. So Camerline and Douglas CPAs have worked with us for 16 years, and they have retired their practice. They're a married couple, and Cindy Douglas and Joseph Camerline have retired their practice. So they've helped us with our nonprofit federal tax records that are filed every May. We are our own LLC, as well as linked in with bylaws to national. So it's really important that we maintain our ability to make sure our records are right. And Joseph had said, you know, Julie, I'm an Eagle Scout. And I said, okay. I said, that makes a lot of sense to me. And so we just want you to know that, you know, as a nonprofit, we are searching for new CPA firms now under the leadership of Andreas and the team. And we really appreciate Kimberly and Douglas keeping their price points low, being a true friend, giving advice whenever you need it, and it just speaks to the quality of who they are. And even though they're not here tonight, I would like a round of applause on their behalf. Okay. And so I have the pleasure of introducing Dr. Joseph Powell. Joe, as he allows me to call him, is, thank you for that, is, you know, really well known in our industry. And from a standpoint of the feedback, this is his fourth presentation in about so many years, or 5 years to our group. And so it's just one of those things that we're very grateful that he's able to fit us into a very tight schedule. The energy transition, hydrogen circularity, and carbon management for the U.S. Gulf Coast is his title, and I'd like to give a little bit of background for him. So the Gulf Coast is one of 3 major global hubs for refining and petrochemicals. This presentation is going to look at the challenges and opportunities in the area and how our area can thrive in leading the clean energy transition, and to address the need for circularity in chemicals, especially plastics. So sustainability considerations are predicted to drive the future investments and the workforce opportunities for our local community. Joe is a fellow of AICHE and served as Shell's chief scientist in chemical engineering from 2006 until he retired in 2020. That's 36 years of industry career. He joined the process development at Shell Technology Center in Houston in 1988. He led his career, or over his career, my apologies, he led R&D programs in new chemical processes, biofuels, enhanced oil recovery, in addition to Hunter's Innovation Group, and served as technology advisor for the energy transition to a net zero carbon economy. Dr. Powell has been the co-inventor on more than 125 distinct patent applications with more than 60 granted. 50% rate, that's amazing, Joe. And has received several industry awards, including the A.D. Little Award for Chemical Engineering Innovation, that's AICHE 1998 award, the R&D 100 award from R&D Magazine, American Chemical Society Team Innovation Award in 2000, the University of Wisconsin College of Engineering Distinguished Achievement Award in 2009, the AICHE Process Development Division Award in 2012, Practice Award in 2017, and Wallace Coulter Award in 2021. He's co-editor and chapter author of the book Sustainable Development in the Process Industries, Cases and Impact by Wiley, published by Wiley in 2010. And he served AICHE in various roles, including chair of the Process Development Division, Spring Meeting Program Chair in 2015 and co-chair in 2012. He was the Chemical Technology Operating Council Representative, Executive Board Programming Committee, Center for Energy Initiatives Board Member, Pilot Plants 12B Area Chair, Shell Gas and Sustainability Topical Chair, and was elected and served on the AICHE Board of Directors between 2016 and 18. He's past chair of the U.S. Department of Energy Hydrogen and Fuel Cell Technology Advisory Committee, or HTAC, and he was elected to the U.S. National Academy of Engineering just last year in 2021. Congratulations. And he had served 2 years on the board of Chemical Science and Technologies. He served as special guest editor of Catalysis Today, Natural Gas Utilization, on the editorial board of Annual Review of Chemical and Biological Engineering, and was Cross-Cutting Technologies team lead and author of Mission Innovation, Carbon Capture Utilization Storage in 2017. Dr. Powell obtained his PhD from Wisconsin-Madison, University of, I just have to say the slang, thank you, and following a BS from University of Virginia in 1978, both in chemical engineering. I'd like to welcome Joe up to the stage, and while he's coming up, I'm gonna have you hold your applause while I give the thank you as we transition to our slides, his slide deck. So again, I'd like to thank him. These would normally be presented afterwards. Thank Joe for his presentation, and let you know that our next meeting is November 3rd at the Bougainvilleas on Westheimer. We'll be talking about improving decision making. It's a leadership presentation on enhancing value in major capital projects. It's by one of my colleagues at Chevron Phillips Chemical. And then there's a pre-dinner workshop on operator effectiveness and special operation regimes, and that's by Schneider Electric. That's Randy Miller, who's the Director of Strategic Business Development. 2 really solid, great presentations. So we have officers that I really want to thank real quick. Dr. Matzakos or Andreas, Joe Hernandez is our secretary, Eureka Diaz-Baloez is our treasurer on her 6th year. Professor Krishnamurti is our past chair. Yasmin McCall is our continuing education officer. Professor Wong from Rice is our position 2 outreach. Paul, or Paul K as I call him, is our communications leader. Dennis Griffith, who we've known, past chair, is human resources. And then we have our YPs like Ram K, Devanshi Wada, Matt Kolodny, Steadfast on K through 12, Rachel Carlton, our webmaster, who I think we all agree just does a beautiful job, Dale Embry and Carol Schmidt for PE Prep, Tom Min for awards as well as OTC, Alan Rossiter for water, energy forums, and SPTC. And Vic Edwards for ECH. I've lost him, but he's here. Tom Rim, John Middleton, Adam Baloez, David Stojan, Trevor Rice, who was instrumental to our meeting execution today, and many others really make our organization work. So thank you very much. On that note, please welcome to the stage Dr. Joe Powell. Thank you very much, Joe. Thank you.
Well, thank you, Julie. It's really an honor to be here today, and quite a introduction to myself. So I guess the lesson is if you say yes and volunteer to do things, you'll be surprised at the number of things you can get involved with over a long career. And AICHE is one of the greatest places to be to do that. So as my time on the board of directors, the South Texas section was always the ultimate performance in terms of local sections. And so I give credit and a thanks to Julie and the officers here today for continuing that strong tradition, and looking out and see the amount of attendance in the audience today and the amount of participation is truly great. It's great for the organization, but again, the volunteer can really do a lot for yourself and for your career. I would tell the story that I would never have been chief scientist at Shell without all the volunteer work I was doing with AICHE and these other organizations. And so if you do that type of activity, extend your knowledge base and network, then great things can happen to you all. So let's talk about exciting things going on in the energy and chemical space. Energy transition, hydrogen, circularity, carbon management, and all of this happening here on the U.S. Gulf Coast, which is one of the 3 largest hubs for petrochemicals in the world. Don't take anything I say tonight as investment advice, and hard to find good investment advice these days. U of H, so Shell has stood up a new institute there, the Energy Transition Institute. The key subjects will encompass what I'm talking about tonight: hydrogen, circularity, and carbon management. It's about students, it's about premier research, but also industry engagement. So if you'd like to get involved, look us up, and we'll look to do great things together in this space, both globally and for the Gulf Coast here. Excuse me. So global energy demand. Looking at a new source of energy going forward into the future here. Everything we've seen to date has been a storable fuel, starting with traditional biomass and then moving up to coal, oil, and natural gas. But if you look at the energy sources that are emerging today, they are primarily the renewable wind and solar, and they are not storable. So that's really going to be a game changer in terms of the energy transition going forward and should give you food for thought in terms of how to manage these systems. So the IEA looks at a pathway to net zero. Shell has published the same in its Shell Scenario publications. The issue that everyone is looking at is, when is peak oil and gas and coal, certainly, and the IEA is saying that's here right about now. And so looking at future energy, we're going to be moving into more of those renewables. You see solar in orange here, the wind in blue, other renewables in light green, and diminishing use of the coal, oil, and gas there in the center, starting at about this point in time. So that's what the energy transition is about. Hydrogen, where is it going to play in this energy transition? So we have a course on that at the U of H, and my boss, Ellen Rossiter, in teaching that hydrogen economy course. If you want to be learning more about that going forward, there's a 3-badge credit class where we get into much more detail than what you will hear about tonight. But the important thing to remember about hydrogen is it's greatly expanded use, not because of the traditional uses of hydrogen, because it's going into new sectors, and that includes mobility, industry. It's replacing a number of features that were previously serviced by gasoline and petroleum, and but then also on the liquefied natural gas side of things. And if you look at where that can be happening, the key point is the energy density of hydrogen relative to electrification and batteries. So you really can't move or store energy in the form of batteries and can't make those movements over great distances. And so you're looking at hydrogen as that vector that can be moving this energy around and storing it. On the bottom left, you see locations in deep blue where you can make hydrogen from natural gas with CCS and reforming. The light green are the regions where you have a lot of renewable resources. And the turquoise, which includes this region, the US, but also the Middle East and a few other locations, are where you can do both. And so those are the resource-rich regions that the world will be looking to for energy, and hydrogen is one of the key vectors to get it into the markets where it's needed. Again, because of that energy density. So looking at roadmaps going forward on what is the prognosis for the emerging hydrogen economy. And so this particular reference from the World Energy Council shows the roadmap of roadmaps. And hydrogen can have a growth from something like twofold, 200%, up to something that may be more than 10 times that in terms of the amount of uptake and future demand that may be seen. A lot of that depends on local energy security issues versus the amount of global trade that we have. If you look at the Shell scenarios, in the most ambitious scenario where the world is the most wealthy is where we have a lot of trade. And if so, there will be a lot of hydrogen uptake in terms of the vector for doing that renewable energy trade. And you will see a large uptake in the use of hydrogen going forward. Now, hydrogen is not new. So discovered many centuries ago, there was a novel from Jules Verne on a mysterious island where they actually predicted the electrolysis of water and using renewable energy to generate hydrogen from water. And so certainly it's been known and a usable vector for some time, but we're now just getting to the point where we can really see it become a commercial reality. I was born at the time of Sputnik, where really the space race challenge and the arms races from the Cold War era became front and center. And so hydrogen was a very important mechanism involved in our early space programs in terms of the clean energy provisions for the space flights from the Apollo missions and Saturn there later. As it went forward in time, going into 2000, the first President Bush said that everybody being born at that period of time would be driving hydrogen fuel cell vehicles by the time they were graduating from college. And that didn't happen. Ballard Energy Systems had come up with the first commercial fuel cell about that time, and there was an assumption that the hydrogen economy would be taking off from then. It didn't happen because the other factors needing to make hydrogen successful had not been co-invented to the point where the cost could be reduced to it be a viable vector. And also, you really have to care about climate change and clean energy to be competitive in this market space. And that's what we're seeing today in terms of what the stakeholders are saying about what they want in terms of future energy. So the US DOE looks at hydrogen at scale. And we're all chemical engineers here. You know the 6/10 Powell rule. But if you can get your end uses up so that your scale of manufacturing can be strong enough, then the price of manufacturing comes down. To do that, you need to see hydrogen going into multiple sectors, as you're seeing here, from transportation to the traditional ammonia fertilizers, also in industry and metals production, and and also in transportation fuels and refining. So that is a key mechanism that's in all of the FOAs and such that are coming out now in terms of trying to launch the hydrogen economy. On the right-hand side, you see that growth rate that the U.S. hydrogen roadmap is predicting, about an 8-fold increase in hydrogen from where it is today, mainly by going into new sectors, which include fuel for industry, the transportation sector, and also in grid support applications. You can make hydrogen, of course, from natural gas or any carbon-based fuel using reforming reactions with water. You can gasify biomass, and you can also bring in electrical power from renewable energy, nuclear and others, and do electrolysis of water. The production can either be central or distributed because of all these different routes to production. And the critical issue is how will this sort itself out as we move forward into this potential hydrogen economy. Many people talk about the different colors of hydrogen. Tonight, I'm only going to focus on about 3 of the key areas. The gray hydrogen is the traditional manufacture of hydrogen, mostly from natural gas today. And the ones we're really focusing on going forward include the blue hydrogen, which would be the same reforming of natural gas, coupled with carbon capture and storage, CCS, to reduce the carbon emissions associated with it. If you're using renewable energy, then that's usually called green hydrogen. Some people call yellow the hydrogen generated on that from solar power, but green is the most common term, implying from the green energy that it's derived from. If it's coming from nuclear power, it can be called pink hydrogen. And then turquoise is hydrogen produced by pyrolysis of methane into solid carbon and hydrogen, and we'll talk about that here in just a moment. White, as we were mentioning earlier, is naturally occurring hydrogen, which has a limited availability, but is being now discovered in small amounts subsurface. So cost of hydrogen, there's an excellent paper from Parkinson at Imperial College that does a nice literature review pre-inflation. So these days you have to adjust all numbers for the inflation values, but up to 2 years back, these numbers were quite good and give a good comparison of estimates of what the different routes to hydrogen would entail in terms of costs, and also some of the details behind that. The thing to keep in mind, though, when you're looking at all these different colors of hydrogen, and especially blue hydrogen, is that the extent of decarbonization can vary quite a bit with that hydrogen. And so you really have to look beyond the colors and say, what is the total carbon footprint that's associated with that hydrogen in terms of the production process by which it was delivered? So these are some of the key reactions then underpinning the green electrolysis of water, which requires a very large amount of energy. Turquoise methane pyrolysis requires quite a bit less, but you have to be able to do something with the solid carbon. And that has to be into a sequestered product. If you're going to put it into tires and make tire black and then burn the tires after 5 years, that's going back to the atmosphere, and so that is not sequestered carbon. Steam methane reforming, again, that's the most prominent way of making hydrogen today. You're making CO2 and then you have to capture and sequester the CO2 or turn it into utilization products, as we'll talk about here in the second part of the presentation tonight. You can also do all of this by partial oxidation and autothermal reforming, and we'll talk about that more in here in just a moment. If you're looking at feedstock choices, you can take anything that has carbon in it and reform it with water and make hydrogen. Of course, methane has the highest hydrogen to carbon ratio, and so it's the natural starting point. If you're into biomass, you have to subtract out the water component of that biomass and recognize that biomass is quite a bit carbohydrates, which means CH2O, and you really have to subtract out that amount of hydrogen that's complex with water in those particular molecules to really understand the effective ratio. But methane, having the highest ratio, is the preferred feedstock for synthesis from the fossil fuels. Hydrogen via biomass gasification. So you certainly can do that. At Shell, we spent quite some effort developing advanced biofuels processes, but the interesting thing is you're struggling with the energy density there. So if you look at that truck on the right-hand side and look at the energy density of wood or wood chips or a typical biomass feedstock, it's coming in 50% wet, drying is difficult, and then much of the molecular composition are the carbohydrates. And so when we were considering trying to develop an advanced biorefinery and the radius that we could collect biomass from, the largest we could do was about 1/20th the scale of the Port Arthur refinery. And to do that, we needed about a truck a minute, as you're seeing here on the bottom right, coming in to supply that particular feed chain. The nice thing about biomass gasification relative to using solar and wind is your capacity factor can be higher because you can store the biomass and use it potentially year-round and have larger operability out of your hydrogen reforming unit. As I mentioned, if you're looking at steam reforming, trying to retrofit existing operations to be to capture some of the CO2 and have a lower carbon intensity, or developing new processes, there are several places in the process where you have to consider capturing the CO2. And so a number of companies have partially decarbonized there and removed a fraction of the CO2, but it can be expensive to remove all of it from steam methane reforming. And hence that has to be taken into account when you're looking at how much decarbonization are you seeing when you're getting what is the so-called blue hydrogen is by steam methane reforming. If you look at changing the process technology, the problem with steam methane reforming is the process side itself is generating CO2, but it's also a very endothermic reaction, and so you have to be bringing in process heat and capturing the CO2 from the process heat side of the equation. If you flip that around and start combusting some of your feedstock in the process by adding oxygen, then you can have autothermal reforming and capture the CO2 in one place more economically. And if you go further to adding a little bit more oxygen, you can actually generate a little bit of excess steam to make clean power and power the whole process. And so that's one of the approaches that Shell prefers with the partial oxidation or gasification approach, where you're adding some oxygen, combusting it inside the process tubes, producing excess steam to generate clean power after the CO2 capture to run your entire process. And it's actually a slightly exothermic side of the process then by looking at that configuration. So the bottom line is that future modes of production of clean hydrogen may differ from the standard SMR that you're used to today. Now with the US DOE has last year announced an earth shot of 1 for 1 by 1, which means a goal to achieve $1 a kilogram hydrogen within the next decade. So that's quite an ambitious goal. You can almost do that with blue hydrogen by steam methane reforming or POX or advanced reforming, carbon capture and storage. But to get truly low CO2 footprint hydrogen, the DOE is looking at moving the electrolysis into this cost range within the next decade. And so you see a lot of activity to reduce the cost of renewable power, but also reduce the capital cost that's involved with those electrolyzers and improve their lifetime and durability as part of the DOE's R&D programs. So this is a graph from Mark Ruth at NREL looking at where technology is believed to be going in terms of what's achievable in terms of cost of hydrogen from electrolysis. It's getting down maybe to $1.73 or a little bit lower than $2 a kilogram for production. But the additional goal of trying to get down to $1 a kilogram is a research stretch target for all those involved in those DOE programs. And so we've seen a lot of announcements about R&D efforts within the last half year and many of us in this audience are probably pursuing those to look at how do we really push the technology development to get those costs down. Some of that, as you see in the duck curve in the lower part of the diagram, can be effective ways of using curtailed power at essentially zero cost, perhaps with a stream factor or capacity factor as low as about 11%. Electrolyzers in China are about 5 times less expensive they are in the West, so trying to understand the modes of production and produce reliable electrolyzers with the codes and standards of the West is another challenge in order to be finding out how to get those costs down. And so it's a very active area of research and development, but also commercialization at this time. If you look on the left-hand side here, we have costs today for green hydrogen and blue, and then gray is projected to get more expensive because of a assumed carbon tax coming forward after 2030. But with the evolution of technology, it's considered that the green hydrogen from electrolysis is likely to be competitive with blue hydrogen by 2030. And so therefore, those making investment decisions today really have to be concerned about what do these curves really look like, and what types of investments do you want to be making now and at what time. So if you look on the right-hand side, a chart from McKinsey and the Hydrogen Council, we're looking at projects that have been announced and are moving forward, the projected path of blue on top and then green on the bottom in terms of what different entities are investing in and moving forward up into the 2030 timeframe. Now, the clean hydrogen definition is getting from a typical 10 kilograms of CO2 per kilogram of hydrogen coming off today's SMR gray technology down to 2 kilograms CO2 per kilogram of hydrogen. And this particular chart from American Clean Hydrogen says you can readily do that on the process side itself. But one really needs to look at the overall supply chain. And one of the items that's been very present in the news, especially over the last 2 to 3 years, is methane leakage. So methane is a much more potent greenhouse gas than CO2. On a 100-year basis, it's gone from about 25 up to 28. But a lot of the NGOs, including the Environmental Defense Fund, are looking at the 20-year global warming potential of hydrogen, which goes as high as 110 times more potent than CO2 on the short time frame. And so they're putting a lot of back pressure on the natural gas economy, and how this impacts hydrogen is looking at the supply chain up from the wells to the manufacturing plant, and having the hydrogen produced bear that burden as well. So if you look in the published papers out there, there are quite a number of different estimates, some of them very severe in terms of their assessment of how bad the leakage rate can be. The one on the lower right from David Allen at University of Texas is perhaps a more balanced assessment than the Horwath and Jacobson paper. But still, with the natural gas coming from the Permian Basin and the difficulty in producing the wells from the liquid production and fracking that's going on there, that is a challenge for this to get a handle on in terms of being able to use natural gas as a source of clean hydrogen. Here's a better study coming out of, this is a global paper on authors from the US and from Europe, looking at kilograms CO2 per kilogram of hydrogen as a function of the different ranges of technologies, and looking at the different global warming potentials for the methane, GWP 100 being the 100-year potential, which is the lower value, and the 20-year being a very high value for methane. But the result of this study is that it's still a challenge for blue hydrogen to become green, or excuse me, become clean if you look at the overall supply chain, considering the production and transport to the production wells. To do this, one really needs to tighten down on the leakage in that supply chain. And so there are quite a number of different entities that are springing up to do that under the title of responsibly sourced gas. I've got a few listed here, but that's going to be very essential for operators in this space in order to get the credits that they're looking for in terms of CO2 mitigation, not only from the carbon capture that's being done at the process unit side, but also in terms of managing the leakage coming out of the supply chain. I would say that if you're using the best production technology, and if you look at the leakage rates that Norway has demonstrated as plausible, the 0.2%, it is possible to produce clean hydrogen using natural gas, and even considering the most severe of the 20-year global warming potentials for methane. So that's something to keep in mind and very important for this region, but also in terms of managing your projects and decision making. There's also news that hydrogen itself can be an indirect global warming agent, and that has gotten the attention of a number of the NGOs. But if you do the analysis of what that impact could be, if one were to replace the fossil fuel economy today with hydrogen and leak 1% of that, then the positive impacts of that replacement would only be reduced by 1.8%. And if you expand that up to a 10% leakage rate for all of this hydrogen being produced, then you're backing out about 18% of the advantage, and that's a much larger number than you could ever afford to be leaking out of that supply chain. So the bottom line is that the indirect global warming potential of hydrogen, it causes consternation in the news, but it's really not that big of an effect in terms of its impact on the hydrogen economy. But you do need to have the numbers in mind so that you can make that argument when necessary. Looking at the alternative to sequestering CO2 is the pathway of methane pyrolysis, the turquoise hydrogen, where you're decomposing methane into solid carbon and hydrogen, and then turning the solid carbon into usable products, hopefully, like the sports car you see on the left, 3D printed at Oak Ridge, or a futuristic building proposed by MIT, also on the bottom left there, or carbon fiber for airplane fuselages. The issue is the size of the energy economy that the hydrogen is flowing into relative to the size of the chemical economy. So the energy economy is more than 10 times greater than the chemical economy. If you really want to do methane pyrolysis and producing hydrogen in a big way, you need to be moving the carbon into applications beyond the traditional petrochemicals and going after substitutions of things like steel and concrete in order to get the materiality to have the two sides matched. You can also dump the carbon into coal mines and forget about getting an advantage out of that, and just consider that to be solid carbon storage. So those are things that people are looking at in terms of methane pyrolysis. I would say that is a technology that can be used in places where you don't have the ability to do CO2 storage. We're blessed with that ability to do the storage here on the Gulf Coast, but there are many places in the world where you can't do that. Moving and transporting hydrogen. So looking at the various vectors, it's traditionally used, moved and stored as a compressed gas. You can do a liquefaction with an energy penalty, but energy density goes very high when you do that. You can look at other carriers like ammonia is being considered, and then a lot of research in things such as the metal hydrides and other solid sorbents. And we'll talk about more of those carriers going forward. Today, you see most of the transport occurring in the gaseous phase via tube trailers or container trailers, and in some cases liquefaction. The Gulf Coast has the largest collection of pipelines in the world, but they're all private, and there's not that much of it. And so pipelines may be more of the vector going forward into the future. Let's consider the bottom left here in terms of how hydrogen plays a role in the vector of energy. So if you've got renewable energy in the form of electrons, then you can make hydrogen, or you can liquefy it, or you can make ammonia as a carrier, or you can make more complex molecules like liquid organic hydrogen carriers, or you can react it with CO2 to make methanol, or go back through synthesis gas and make hydrocarbon fuels. So as you go up that chain, the convenience of handling the fuel is improved, but the cost goes up and the efficiency of the energy use goes down. So those are considerations to take in point in terms of looking at hydrogen as a vector. The typical way to consider long distance transport is by making ammonia, which is very stable. And the way to do that is to actually generate your hydrogen by electrolysis or by steam methane reforming, and then run the traditional Haber-Bosch synthesis process. The direct electrochemical ammonia synthesis is challenged because of solubilities and rates. And so Haber-Bosch still comes into play in terms of the second step of that conversion from the synthesized hydrogen. And so there's a lot of consideration on use of ammonia as that vector on long distance shipping routes. A number of the projects proposed commercial already today, more than 370 or so proposed worldwide, and many are considering ammonia as the vector to be moving hydrogen around as that vector. Now, one of the 10 worst days in Houston's history was the day that an anhydrous ammonia truck fell off of the 610 loop up Highway 59 a little bit from here, and spilled, killed 6 people immediately, damaged lungs, and for about 100 or more others. And it's an example of the toxicity of ammonia as a vector, and that needs to be taken into account in terms of how it might play into the future economy. And so one way to counteract that is to consider use of liquid organic hydrogen carriers. And so these are essentially aromatic molecules, the simplest one being toluene, which you can hydrogenate to a cycloalkane, and then take that to market and apply heat and dehydrogenate to recover your hydrogen. So methyl cyclohexane toluene being one combo, and another one being the dibenzyl toluene perhydrodibenzyl toluene, which has the advantage of being very, very low in toxicity and non-flammable. So Toyota is looking at the methyl cyclohexane option. You see some of the process equipment in the upper right there needed for hydrogenation, dehydrogenation. And that's the lower cost toluene molecule as the hydrogenated carrier, toluene being widely available. The other ones, the multi-cycle rings, are a bit more expensive and more of a challenge, but Hydrogenious being a company that's looking at using the dibenzyl toluene for transport down the Danube to get hydrogen into Germany because of the safety that's afforded by that molecule. If you look at the cost economics, you see the numbers all over the place in terms of who is doing the calculation and the scenario assumption about the hydrogen carriers. So again, ammonia, methyl cyclohexane, or gaseous hydrogen are calculated here on the right-hand side, and going all the way to reacting a source of CO2 with hydrogen to make methanol as a carrier is also in consideration in this set of numbers calculated from the DOE. Affordable hydrogen costs. So if you're going to develop an economy, you look at why not go after the highest economic value use cases first. And so here's a waterfall plot showing what that would be. Certainly the existing chemical feedstocks being at the top, data center storage being at the very top. So Microsoft can go after very high priced hydrogen for its stakeholder base. But if you look at the value proposition, the proposition in the transportation space by cars and trucks is where the highest value is. You can command something on the order of $3 a kilogram production and $5 a kilogram dispensed, because 1 kilogram of hydrogen is equivalent to a gallon of gasoline or diesel, and therefore you can be competing hydrogen in the liquid fuels market if you can make it for something around $3 a kilogram. If you look on the right-hand side, and if you're trying to replace utility power or industry power, then that's a more severe cost challenge for implementation of the hydrogen. The other thing to keep in mind with hydrogen is we've to date been working with fuels, and where electricity has been made, it's been predominantly made by combusting a fuel and then running a cycle to generate electricity. And now with renewable energy, you're actually getting access to the photons or the electricity and wind-driven electricity first. And if you want to make a synthetic fuel, that's now a derivative off of the primary energy source. And so with hydrogen, you really have that opportunity to be taking those electrons and be using them more efficiently in electrochemical devices or fuel cells and not be combusting them in heat engines. And so that's an important consideration to keep in mind in terms of trying to maximize the efficiency. So a battery versus a fuel cell. We're all familiar with batteries. You're putting in electrical power, storing it, and then taking it back out as work. You can do the same thing by running a reaction in that electrochemical device by feeding in hydrogen along with oxygen, electrochemically reacting it to water, and take out electrical energy as work on a continuous basis. So if we look at what hydrogen fuel cell vehicles are, they're really electric drivetrains where the fuel cell is providing the electricity to provide a continuous source of that electrical power generation. The car you see on the right-hand side is a big step up from the prototypes that we were seeing back in the 1970s, and these are now commercial vehicles and starting to enter the marketplace. The other critical thing about this is that these, both the hydrogen fuel cell vehicle and the battery electric, are zero-emission vehicles. There's no criteria pollutants coming out of the tailpipe. And at Shell, I worked on biofuels for more than a decade, as many other companies were involved in that. And the biofuels are nice from a CO2 management point of view, but if you put them in a combustion engine, they're still producing smog, particulate matter, and all those things that people care about in terms of air quality and health. And so therefore moving to electrification via hydrogen fuel cells or battery electric is really where the stakeholders are asking the transportation sector to go. Not just CO2, but also the air quality and criteria pollutants. And in that regard, looking at the success story of hydrogen and fuel cells in the US. This is a typical slide shown by Sunita Satyapal who runs the fuel cell office for the DOE as a scorecard showing the progress in the industry. And the stellar example is the forklift example, which has been expanding so rapidly into hydrogen fuel cells that it's difficult to keep up with the number. So I think the 40,000 you see on the left is now 47,000 and above. And the story behind that is that if you're running a warehouse, you want a zero-emission vehicle for your workers. And so diesel is not effective. And the industry looked at electrification as the first thought. But it takes time to recharge those forklifts, and their power performance goes down across their duty cycle. And so Plug Power and others came in with a hydrogen alternative to that using fuel cell-driven forklifts and essentially took over the market. So what you see now, and that's with no incentives for clean air quality or CO2 emission reduction, but the commercial advantage was you needed 10% fewer forklifts, you could maintain them running throughout the day because of the rapid refueling relative to battery recharging. And hence, with that value proposition, they are now the dominant way that goods are moved at Home Depot, Walmart, Amazon, and the like warehouses. And so Plug Power is looking to leverage that business model in terms of moving into the larger vehicle transport space. Let's talk more about efficiency in the transport space. So this is a diagram from Shell, starting up on the left-hand corner at 100% energy, and going down there, numbers 1, 2, and 3, in terms of how much of that energy ends up in the wheels drive of electric vehicles from either independent sourcing or the grid. 4 and 6 are the similar equation if you were to start with gasoline or diesel and put them into trucks and cars. And 5 is what you can do with hydrogen. So it's less efficient because you need energy to make the hydrogen, regardless of your method of synthesis. But it is about half the efficiency of just directly using the electric energy with storage in a battery. If you further try to make synthetic fuels by reacting that hydrogen with CO2, you get into the range of the 7, 8s, and 9s and 10s if you're going to direct air capture of the CO2, and your efficiency is going down even further. So what I like to say, if you've got a wind or a solar farm, you can have one of them to supply a given supply chain of battery electric with the efficiency of that storage. It'll take twice that number if you want to go hydrogen and use fuel cells, and it'll take 4 times that if you want to make a synthetic aviation fuel or the like. And so you have to have a very good reason for wanting to do anything other than electrify. But the reason that you do need to do something other than just electrify is because of that power density. There's a number of transport applications that just can't run the lower power density as afforded by batteries. And so hydrogen is seen as a vector. Anything above the tiniest of vehicles and up into some of the smaller side of the aviation space. Ammonia perhaps for that tanker you see in the upper right. Perhaps synthetic aviation fuel still needed for the jumbo jet. But we saw, because of the commercial refueling advantage, hydrogen is still advantaged on the left-hand side, even for the smaller vehicles like the forklifts. So the OEMs are looking at this equation. McKinsey and the Hydrogen Council have a cost curve on the left saying that hydrogen trucks can become competitive with diesel by 2030. A number of the manufacturers are considering this space. Scania was saying, I want to electrify all the trucks in Denmark, and I want to avoid having to do a hydrogen rollout. But last summer, their customers came back to them and said, these electric trucks just can't perform the duty cycles that we need, and we really want you to be investigating that space. GM and Navistar being in that space for quite some time. Volkswagen made a statement that they were only going to be providing electric vehicles on the small passenger side. But again, they retracted from that a little bit last summer, and they're looking some of the duty cycles evolving in the passenger car space. So it's a very dynamic field. You need to look at what is the advantage beyond just the clean fuel and low smog that goes with hydrogen fuel cells or electrification in general. And the answer is these motors and drivetrains are much simpler for the electronic devices and drivetrains than they are for the internal combustion engine. So if you look at a diesel truck, you're eliminating more than 7,800 pounds of drivetrain, fluids and lubrication systems, and also air pollution control devices. And so that's a big advantage. It also saves on the maintenance costs because they're simpler devices and there's less weight to be carried around. Such that all that has to go into the total cost of ownership calculations in looking at these trucks, and even the passenger cars. This is a chart that shows the refuel times versus recharge times of heavy-duty trucks, and the answer is that a larger size truck would take up to 2 hours to recharge for a battery version, and only 15 minutes for hydrogen. And if you look at labor costs being 42% of a typical trucking fleet, the idle time of that truck plus the labor cost is a really big consideration that would drive fleet owners to want to be running hydrogen fuel cell trucks because of that advantage. Buses, trains, ships, and planes. So it translates into other aspects of transport as well. This was a set of papers I was involved with Stanford Energy looking across the space. And many of the entities providing these segments of transportation, especially buses and trains, looked at electrifying first, but they found again that the rapid refueling was an advantage. And if it's a train, you really don't have the power density to be able to make it from one stop to the other using batteries for many of these routes. And so you have to consider installing either an overhead catenary line or a third rail, which is very expensive and can be unsightly, whereas you can do it directly by using hydrogen on board with a hydrogen fuel cell. And so that they found that hydrogen fuel cell trains can be more than competitive with electrification on many types of services and routes. Similarly, planes are considering electrifying in the light duty sector, but hydrogen for the somewhat heavier sector of those. And then for shipping, you really need either a liquid fuel, a biofuel, or perhaps ammonia or liquid hydrogen for the energy density to make those types of routes. In terms of grid services, so that's also evolving despite the lower value added. California is looking at going all renewable energy. There is an issue. Anyone who's done the scenario modeling finds you can't go to 100% renewables. You need to have at least 10% dispatchable power. And stored hydrogen can be that dispatchable power made off of that renewable energy. So one of the commercial test markets for that is High Deal LA, where they're looking at making hydrogen from renewable energy in Nevada and then storing it there. The reason being that's the only salt dome in the western part of the US where you can brine leach the salt cavern and do large volume hydrogen energy storage. And so that will be gridded back into LA to provide commercial scale renewable power with storage to be providing that on blending in on a 24/7 basis. To do that on a large scale, you don't use fuel cells with the hydrogen, but you really put it into a gas turbine. And so companies like Mitsubishi and GE are developing 100% fired gas turbines that can effectively combust the hydrogen, not make a lot of NOx, and then provide that grid support service. So where's the hydrogen economy emerging? Everywhere in the world, but the markets for it are really quite a bit in Europe because of the legislation, and Japan because they're energy poor. And then you see a number of the research-rich regions looking at doing green or blue hydrogen projects and supplying to those locations quite a bit through ammonia as the long-distance vector. This particular McKinsey study had 228 announced projects. I know our colleague for the hydrogen economy course says that's more like 370. And so it's a really very hot area in terms of scouting projects to be supplying that hydrogen vector, especially with ammonia as a carrier. Of course, we can do that from the US Gulf Coast region as well. We have abundant natural gas resources, ability to do the CCS, and also the wind resource from West Texas, solar capabilities as well. We have a showplace project here at the University of Houston looking to recommission offshore facilities to be involved in that generation space. And so certainly the Gulf Coast and Houston has every ability to qualify for one of those hydrogen hubs, which the FOA has just come out, and delivery needed by coming into November in terms of concept papers for what those hubs might look like. So a very exciting opportunity for the Gulf Coast area to be emerging as a player in this market. That covers hydrogen, and again, sign up for the course. if you want to hear the 15-week version versus the short synopsis. We'll talk a little bit about circularity because it's related to the sustainability argument. These are some charts from the Ellen MacArthur Foundation about dealing with things like ending plastic waste in the ocean. So Shell and Dow were both founding members of the Alliance to End Plastic Waste. Like climate change, this has become front and center with quite a number of stakeholders. And so let's step through quickly about what that entails. The current plastics and chemical economy is now mostly linear. You take in petroleum, maybe perhaps natural gas, you refine and you make products, you use the products, and then you send them to end of life, mostly into landfills or sometimes into incineration in a linear mode. And so the objective is to move to a more circular mode where you're actually reusing a lot of those molecules as the dominant source of rejuvenating those materials, and then you're making them up with renewable or neutral CO2 sources, which would come from biogenic CO2 or direct air capture of CO2 or green plants, biomass, who has done the capture for you as your makeup to the chemical economy. If you want to do that, you have a lot of cycles and chains to consider, and what's mostly forgotten about is what happens on the back end at the end of life of these products, and how they biodegrade, go back into the atmosphere, or might be reused to redo that economy. So you really have to look at all the sources and sinks and all of the cycles in terms of how those materials can be rejuvenated. Ideally, you would like to selectively recycle molecules and not have very many of those materials go back out as CO2 by biodegradation and then have to be captured and taken back from CO2, which is less efficient. But we really need to pay attention into what's happening on the back end, including incineration or landfilling in terms of end of life for the materials and looking at these cycles. So my colleague Jean-Paul Lange in the Netherlands wrote some nice papers over the years looking at what are the bond strengths in the polymers that we're using today and what is the best mechanism to recycle. Do you have to do mechanical recycling, maybe downcycling in order to have a future use? Or if you're looking at nylons or polyesters, they can be depolymerized back to monomer relatively easily. And that would be an atom and energy efficient way to get back into the recycle economy mode. So the Pew Foundation has looked at what would that future circular economy look like in terms of how these different circularity aspects would come into play. Some of it is to eliminate the need for some of these materials to reduce the amount of materials demand. Other forms of recycle in terms of paper, which is relatively easy to recycle in terms of what some of these products are made out of. As you go down into the greens, you're looking at mechanical recycling of polymeric materials, and into the yellows, you're looking at what happens with some of these plastics and more difficult polymers that in order to get back to the product performance that you had initially, you have to consider reformulating them from scratch or at least depolymerizing them back to monomer in order to regain the property characteristics that you need in those products. And so the yellows are looking at the chemical conversion, the landfills and incinerations going forward. And then the pinks there in the bottom is the mismanagement, which given the complexity of recycle is expected still to be happening going up into the 2040s. So if you're looking at the makeup feedstocks for a circular economy, as I indicated, you could look at recycle of CO2 or going in with bio-based feed materials. And currently involved in a National Academy study to look at what is the opportunity for carbon CO2 capture and utilization to be making up that recycle into the circular economy. And to do that, one looks at all the different types of chemical products that can be formed, the amount of energy and the amount of hydrogen that's needed to bring hydrodynamically degraded CO2 back into the hydrocarbon product space with or without oxygen. And the power and the hydrogen needs are quite extensive. So those others doing the math find that if you're capturing CO2 and trying to bring it back into hydrocarbon products, you're really using an excessive amount of energy relative to what would have taken just to store it subsurface if you're doing CO2. And so the net lesson from this, it's probably easier to be getting those products from bio-based conversions and biomass than it is from direct air capture CO2. And if you got into a situation where carbon capture and storage was effectively did not happen because of stakeholder back pressure, then you would get into an economy where could be more carbon capture and utilization into products. But the energy you need is quite extensive. And so a lot of that has to do with the fact that to be sustainable, you need to be capturing that CO2 from the air at 450 parts per million versus taking it from higher concentrations in flue gases. So to understand that, this article from the EU discusses the supply chains and what happens with plastics once they come to end of life. And it's a little bit difficult argument to understand, except that the fact that we don't have good sorting and segregation for end of life of materials, and therefore there's a good chance that what's going into landfills today will end up being incinerated, and in Europe 80% is incinerated already. So the fact that there are plastics like polyethylene that have perhaps thousands of years life in a landfill, it doesn't get a chance to exist there because there's also table scraps from dinner tonight that'll end up there, and those table scraps are going anaerobically and digesting to make methane, which is a very potent greenhouse gas. And so a lot of the overall circularity management uses incineration to deal with that problem. Some of it uses trying to capture and use the landfill gas, but in general, more and more difficult to maintain and use landfill sites, and more incineration going into the future, which means given the problem with segregation of plastics waste, a lot of those plastics end up getting incinerated in that economy. And for that reason, the makeup needs to be biogenic CO2 coming from either direct air capture of the CO2, or for something like the off gas of a bioethanol plant, where that's a bio-CO2 molecule that can be low cost captured and utilized. So that's where the EU is getting in terms of circularity and what would be allowed in terms of considered to be a green sustainable chemical product, and a lot of pressure in the US to be considering the same type of standards given the international trade of chemical products. So this was all part of a mission innovation right after Harvey in 2017 in terms of having that discussion, and continues on today in terms of looking at what to do about that circular economy. Cement plants are interesting because the CO2 coming off of limestone is unavoidable, and that may be a target for something that can be utilized. The fuel needed to calcine that limestone is fossil and can be avoided, so about half of the emissions off of cement manufacturing may represent CO2 point sources that could be utilized because it's really unavoidable CO2 needed for building materials. So that's really what's happening in the circularity space, looking at the different sinks and sources of makeup carbon products going into that circular economy. If you're starting with biomass, you can make just about anything from biomass in terms of the components in the current economy, and you can do the same thing with CO2 by reacting it with hydrogen and using syngas chemistry. So both are equivalent in terms of the breadth of products that can be made. So my colleague Jean-Paul Lange, looking at what that future circular economy is likely to look like, and showing one of the first simulations of what those different sources may be. But the gray shows the continued use of fossil feedstocks for the hydrocarbon chemicals industry. And then the light blue being the mechanical recycle, the deep blue being the chemical recycle, including the depolymerization, and the light and deep greens being the bio-based biomass type feedstocks makeups, and then the yellow solar being the direct air capture solar converted type of materials. So that gives you an idea of what some of that may look like going forward into the future. In terms of managing the waste facilities, pyrolysis is an emerging technology, more efficient than gasification, and incineration in terms of recovering value from those materials that are there. So to summarize, circular economy is orthogonal to the climate change problem because it takes a large amount of energy to recycle hydrocarbon materials. And unlike aluminum cans or paper, which can be very efficiently recycled and cost effective, it costs more money and energy to be recycling the chemical economy. But certainly the stakeholders are asking for that. And so that is one of the exciting things that the U of H Energy Center will be working on, and many others to be making that happen. And hydrogen plays an important role in those conversion reactions. In terms of priorities, you're better off using all your new clean and renewable energy first to decarbonize the grid because of that efficiency argument I made earlier. And if you start going with hydrogen instead of electrification, it takes twice as much energy to use hydrogen in a vector. If you're making these chemical products, it takes up to 4 times the amount of energy. And so grid decarbonization is a one-for-one trade-off and is certainly the thing to be looked at first in terms of how to use a given amount of energy. So with that, be happy to hear from you if you're interested in working in that space. And again, exciting things evolving in many directions, U of H being one of them. And look me up if that's an interesting area for you and your company. And with that, thank you for your attention tonight, and thank you for the opportunity.
Thank you, Joe. Joe, I'd like to thank you on behalf of the section. My opinion is it's at least 40 hours of research per slide, maybe more. If we were just to read up on the research that's already been done, is what I mean by that. So it's really a workshop condensed in an hour's time, and we're very grateful. Because of the late hour, I'm going to refer questions to Joe one-on-one. And let everyone go ahead and wrap up for the evening. There's so many questions that we could ask that it could go on. So I just want to check with the audience that that's okay. I've seen some nods. Okay, so thank you, Joe, on behalf of the South Texas section. It's just amazing what you can pack into your presentations, and we're very grateful.
All righty, thank you.